Here we have a graph of potential against distance from the center of the sphere. It's a conducting sphere with radius r. Inside the sphere, any PD would cause the charge to flow, so you end up with 0 PD inside the sphere, meaning potential is constant. Away from the sphere, the potential drops following V equals kq over x. What will the graph for electric field strength against distance look like? Start with the relationship. How is potential related to field strength? What is the equation? If you said E equals V over X, then think again. E is the negative of the potential gradient, so that means E equals minus delta V over delta X. Not r in this case because r is the radius, x is the distance. Be careful about that. Don't just quote things that you remember from before. Look at the actual question and make sure you're answering this one specifically. So, now we got that, we need to sketch the graph. Pause the video, have a go at it. Inside the sphere, with x less than r, what is the gradient of V against r? It's 0, isn't it? So let's plot at 0 here. Yep. Don't worry if it looks odd. Just follow the maths. At the surface, field strength will be maximum. Then it will drop off. Like so. I'm not worried about the exact gradient, but I happen to know it'll be steeper than the potential one because E equals kq over x squared. I also know it won't reach 0, so I'll be careful there. It can get more complex looking at two charged objects, such as this one, for example. What can we tell from this graph? Well, if you look at the field inside the objects, what does that tell you? Yep, so the two objects are conductors because the field inside is 0. The two objects have the same polarity. We can tell that because there's a point where the field strength is 0. Imagine the field here due to the object on the left. Let's call that one A and the other one B. So the field here due to A, if A is positive, would point off to the right. If B was also positive, then here in the middle of the field due to B would point off to the left. So they can cancel out because they are in opposite directions, somewhere in between. Also, remembering that the electric field strength plotted here is the negative of the potential gradient, we can see that the potential is changing most rapidly here at 11.4 centimeters. This is the largest value of E, so that's the largest change in potential. And we can also tell that the rate of change of potential has a minimum value here, here, and here, where the field strength is 0. So if I try to plot potential against x, I'm going to assume both are positive. And so I have a high value for A up to 1.4 centimeters. And I have a higher value for B from 11.4 centimeters. Then a U shape with this minimum at 8 centimeters. Oh no, 7.9 centimeters by the looks of it. And that gives us the 0 gradient at these 3 points like we wanted. and the potential gradient is steepest at 11.4 centimeters. And that's the sort of thing you should be able to understand and interpret if you really understand what's going on with electric field strength and potential gradient and potential difference. When you have got the hang of that, we'll start to move on to some proper uses for this, capacitors.